change tact a little bit in that I think that there's a small disconnect between the way we discuss collisions from the standpoint of conservation of momentum and the way we interpret what it means to be in a collision. So let me start by emphasizing something that I think has been lost in our discussion about collisions. Collisions are about impulse and Newton's third law. In fact, what I would argue is that a collision is the quintessential example of Newton's third law. And it explains why momentum is conserved. So no matter how two objects interact, a collision A binds two or more objects together I want to get it written before I try to say it. It binds two or more objects together through a third law pair. I say two or more because you can have multiple pairs at once. But that's the first thing that has to be understood here, is that there is a third law interaction between two objects. And again, you can have multiple pairs interacting at one time, which is why I need to say two or more. But a collision is a Newton's third law interaction. Now, there's the part of me that wants you to know the broader, the broader physics here, and there's a part of me that wants you to pass the exam. Please be aware, you don't have to have contact for a collision to occur. At the nuclear level, there's no contact for collisions. A particle doesn't touch another particle. They never get close enough. But we still see scattering of particles. I mean, if you look at something like a lot of chemistry involves scattering experiments. In a scattering experiment where a beam of particles is fired at perhaps a target, there's never contact between one particle and another, but they experience a collision through the Coulomb's repulsion. And it's because of that you get a collision. They are each experiencing an equal and opposite force, which is a third law pair. And it is that force that exchanges momentum between them, which brings us to part B. This is about impulse. In that we know that, and I'm going to do this in the simplest possible terms, it is a force times time. It's impossible for two objects to interact without them interacting using the same size force and for the same amount of time. I mean, if you put your hand on your desk, there's absolutely no way you can touch the desk for a longer period of time than it can touch you. The moment you take your hand off the desk, you're no longer touching it. It's no longer applying a force to you. And you're no longer applying a force to it. And by Newton's third law, the force has to be the same size. And because contact has to exist for the same amount of time, each object must experience the same change in momentum. They must. There is no physical way that one object can have a larger change in momentum than another if they're in contact. Which brings up C. The net change in momentum of a system has to be zero. It has to be. If Newton's third law says that for each interaction there's an equal but opposite force, then by consequence, for each interaction there has to be an equal and opposite change in momentum. So when you add up all those changes in momentum, you're going to get that the net change in momentum of your system is zero. Now, I could go back through all of this and repeat it for torque, because it's the same. There is a angular impulse. It wouldn't be force, but an angular impulse would be a torque applied for a certain amount of time. How would it change? Well, it wouldn't be a change in linear momentum, but it'd be a change in angular momentum. Is it still a third law pair? Yeah, a third law torque. And lastly, the net change of momentum of the system would still have to be zero. Now, the biggest problem with dealing with collision questions now that you have a more sophisticated understanding of these interactions, is that we are always seeing a torque and a force in every interaction. We have to decide which ones are more useful in predicting the outcome of the interaction. And here's where I want to change the script on this a little bit. These theories are not theories in that I want you to understand what a system is and what conservation of momentum is and all of that. These theories are here to help guide us as to making predictions about outcomes. So we don't try to say, okay, is this one where I use energy or is this one where I use momentum? We're using them all the time. What's going to best help me figure out the outcome of a particular example? Now I'm going to throw down an example that is, and this is just a start, but it's not going to look like a collision. But the question is it a collision? Can we use the rules that we know to try and manage the question? So imagine a wagon that's just rolling across some kind of level surface. And let's just make this easy. Nice level surface, no friction, no problems here. I don't have to worry about the moment of inertia of the wheels or anything. It's just a wagon moving to the right, has some mass, capital M. And since we're in Florida, it is possible to have the sun shining right here and to have it raining right here. So let's say our wagon transitions from the side of the street where there's no rain to the side of the street where there is rain. The wagon's going to start filling up with water. Now, can anybody make a prediction of what's going to happen to the wagon as it fills up with water? It'll slow down. So I don't think there's a lot of physics necessary to understand that the wagon's going to slow down. I think we would probably chalk that up to common sense. But what if I asked you how much water would it have to collect in order for its velocity to be reduced by a third? Could you solve that question? And could you apply the rules of impulse and momentum to solve this problem? It sounds very much outside the bounds of what we've talked about, but imagine we have raindrops coming into the bucket or into the wagon. It seems to me that after a while, I would begin to have a puddle of water forming inside the wagon. So how much water would I have to collect for the velocity of the wagon to be reduced by a third? If I wanted to think about it from the standpoint of just a single raindrop, if a single raindrop is falling, it does have a vertical momentum. Does it have a horizontal momentum? I got Ricardo shaking his head, Melissa shaking her head. I think we can all agree that if it's just a standard kind of Florida, afternoon shower, not one of our thunderstorms, but just, the rain falling straight down, it would only have a vertical velocity, but it would have momentum. Now, and this is where I don't want to split hairs on it. I want understanding. And it's hard for me to know whether this is coming through to all of you. So let me try and emphasize my next statement by saying that I'm not trying to confuse anybody. We're trying to understand the interaction here. Because I think that the wagon is going to apply two forces to the drop. I think the wagon is going to push upwards on the drop. That'll be a force that the drop is going to experience by the wagon. And by Newton's third law, there's also going to be a force on the wagon from the drop. Those have to be equal and opposite forces. I think it's clear that this force will change the momentum of the drop. It's vertical momentum. It's going to stop the drop. Otherwise, the drop would go through the wagon and into the ground. Now, is this drop going to change the momentum of the wagon? It's vertical momentum. You see, we have to recognize that momentum's a vector. So when we talk about change in momentum, we need to be careful about what we believe is happening. The wagon is going to experience a force from the ground that's probably going to prevent the wagon's vertical momentum from changing. Can we at least all agree on that? That the ground is going to push up a little harder to deal with the fact that it's stopping the raindrop. But I also believe the raindrop does not have a horizontal momentum until it reaches the wagon. When it reaches the wagon itself is going to push the raindrop with a force to the right. Either the wagon will or other water in the wagon will. But that means it's going to apply a force to the wagon to the left. Now, this is a horizontal force. And because it's a horizontal force, there is nothing acting on the wagon to absorb this force, to account for this force. This force will change the momentum of the wagon. While the force on the drop is going to change the momentum of the drop. So I'm using this problem because I think this problem is easy to visualize, and I'm using this problem because it's actually relatively easy. When we look at the grand scheme of things, there is a before picture and an after picture, which is how I always told you to kind of draft out how we look at these problems. I don't know how much water I have to collect. I know that all of the water I'm going to collect has no horizontal velocity until it's in the wagon. So right now, the momentum of the system is mv. But after a while, I'm going to have the wagon plus some mass of water. And all of it is going to have the same velocity. I want to know when the wagon has lost a third of its velocity. Now, this is one of those things where students in a hurry don't hear the nuance of the words. Like I told you, the AP exam has increased the number of words. You're seeing that. In later exams, ones that are more current, the word count is in some cases gone up by a factor of 4. They're asking the same questions, but they're very verbose. So a phrase like, the wagon now has a third of its velocity, or the wagon has lost a third of its velocity. There's subtle differences. It's probably only worth a point in the whole grading scheme, but saying that the wagon loses a third of its velocity means it now has 2/3 of its original velocity. but it's just the change in one prepositional phrase. It's subtle. But I don't think there's a problem here. I think you guys can probably now figure out what the mass of water has to be. You know, the V's cancel out, and I'll get 3/2 m equals m plus mass of water. I will subtract m from both sides and get 1/2 m equals the mass of water. Meaning the wagon will have its speed reduced by 1/3 when it's collected half of its own mass. Now, this is still just the same kind of inelastic collision question we've seen before, but asked in a way that's designed to trip you up, to design maybe not to make you think of momentum. But it's a momentum question. Now, this is my introductory question for a review on linear momentum. I want to pause for a minute because we've been going at it. I'm going to hit these high points for just a moment. Somebody needs a break. I don't know who it was. I didn't look. But there are quite literally lots of different types of collisions. But they're all going to boil down to more or less 5 different styles on the AP exam. The first and most obvious is a standard inelastic collision. We've talked about that just now, but let's make sure we understand that in a perfectly inelastic collision, the objects join together due to the course of the collision. Momentum's conserved, but in these we know the kinetic energy will not be. Mathematically, we can also have collisions in which the objects don't join together, but still don't conserve energy, conserve kinetic energy, meaning during the course of the collision, there's an exchange in momentum and likely an exchange in energy. But there's also a loss of kinetic energy in some fashion or some shape, usually not understood in the question. So generally that tends to be a creation of heat, light, sound, deformation of the materials. But unless you are specifically told or have means to understand, you should never assume that the kinetic energy is conserved. You should almost always assume that the kinetic energy before is greater than the kinetic energy after. So there's going to be a loss of the kinetic energy to the environment. Unless the word elastic is specifically used, we know that the energy is lost. However, those are the 3 basics, and we know about those 3 basics, but we also know that AP likes to play around with those basics by throwing in a means of figuring out what happened to the energy. These are the ones that tend to trip you guys up, and we've seen a few of these. The one where maybe there's a spring on one of the cars, but one of the cars has momentum. Now, in a problem like this is still going to be a momentum problem. We're still going to have an interaction between the 2 objects. But in this interaction, we have the ability to trace the pathway of the energy, suggesting that, and I'm not going to put kinetic energy here, but that there will be a point, perhaps, where the 2 objects are connected by the spring and have the same velocity, but there also might be this point later in the problem where the objects separate again with independent velocities. This problem doesn't have to be dictated as an elastic collision, but it is. In this question, we are able to figure out what happened to the energy. We have a conservative force. And whenever a conservative force comes into play in your problem during an interaction, you can trace and conserve the energy. In this problem, mechanical energy is conserved. So you have this middle point where the energy has been transformed into a form in which you can get the energy and extract it back out later. And it's important to note that at this moment, both objects have the same velocity. This is an intermediate position in the problem. So this would also represent the moment that the spring is at its maximum compression. That's the kind of question they're going to ask. This is at its heart a collision question and a means to represent how the energy is conserved. We've seen this kind of problem in two different ways. One using the conservative force of a spring, and one using the conservative force of gravity. Do you remember this? The frictionless surface and a block and a ramp where there is an intermediate condition where the block and ramp were joined together, where the block had gone some height up onto the ramp, but now the system had potential and kinetic energy. And then afterwards, the ramp and the block separated. In these two examples, they don't have to explicitly state that this is an elastic collision, but it is. We are able to trace the mechanical energy, and therefore the result of this collision is going to be one in which we have mechanical conservation of kinetic energy. The kinetic energy here is the same as the kinetic energy here and can be treated as a regular elastic collision. So these represent all of the possible one-dimensional collisions that we have. But we know the AP exam is really not going to have the time for just this. In the last 5 years, the only time the AP exam has used a collision question like this, it's been attached to a lab question, where they've asked specific laboratory information about the collision, giving you data, perhaps about the velocity or the force, reminding you that during the collision, which I've represented as these lines here, during the collision, this is the point where the impulse occurred. And generally it happened very fast. But if they give you enough information to calculate impulse, then you can compute how much one object's momentum changed. It's your job then to apply that to both objects. And often they'll give you a graph, a force versus time graph, with usually something like that in the middle, suggesting that you estimate the area under this graph to represent the change in momentum of the system. This has been pretty common in the last couple of years, and this is going to be our first practice FRQ next week when we start looking at one-dimensional examples. But with us not having our full set of data, our full set of content, I think we need to come to grips with the potential for there to be a two-dimensional collision question. This too is part of our curriculum. We tend to ignore it. There hasn't been a two-dimensional collision question on the AP exam in over 10 years. Wouldn't it be a wonderful year for them to throw that one in? Now, the reason we tend to not see two-dimensional collision questions isn't because they're so terribly difficult to understand. It's because they're complicated. Not mathematically so much, but it takes quite a bit of time to successfully compute a two-dimensional collision. Even in its simplest form, and this is its simplest form, in a two-dimensional collision, there has to be understanding that the momentum before is equivalent to the momentum after. Generally, in a two-dimensional collision, we are almost always interested in looking at the net momentum of the system after the collision having to be equivalent to the momentum of the first object in the collision. What this means is that dotted line I just drew represents the momentum's direction after the collision. So any momentum off of this axis has to be equal and opposite. Generally, that's how these problems are solved, looking at the y momentums, recognizing that they have to be equal and opposite, and those cancel out, giving you a way of calculating perhaps the scattering angle. Now we're going to look at a bunch of video of that because I sat and played pool over and over again to be able to demonstrate the way these collisions look and some easy ways to make some of these calculations. Which brings me to the last part of this. I believe our most likely problem in which we should be prepared is the problem that involves both angular and linear momentum. This is the last thing we kind of learned. This idea that you can have an object that interacts in such a way where the shape of the object matters during the interaction. Something like this, either with a fulcrum or without. With a fulcrum, meaning one of the objects is fastened to the ground, the linear momentum will not be conserved because the fulcrum acts as an external force on the system. But that force does not apply a torque. So if there's a fulcrum, angular momentum will still be conserved. But the fulcrum becomes the point of reference for angular momentum. If there's no fulcrum, then there's no external force, and immediately two things are quite evident. The linear momentum will be conserved, but the linear momentum has to be measured relative to the center of mass of both objects. Meaning after this collision, both objects will have momentum. But likely, and not likely, it will have to be that momentum is to the right, because that's the direction of the current momentum. On the other hand, angular momentum will have to be conserved as well, which means both objects could be rotating after the collision. Without a fulcrum, the center of mass of the object with extension becomes the point of reference for angular momentum. That's a place where I would like to spend a little bit of time on it, and I'd maybe like to do this next week, Thursday. And that's the rocket problem. The rocket problem presents us with a unique opportunity to talk about the rate at which fuel is consumed. These problems are different in that we've almost always assumed that the mass of our objects remain the same all the time. But a rocket's going to consume 90% or more of its mass while accelerating its payload. In these problems, we can't assume the mass is constant. So the rocket problem will be our final one because the rocket problem requires integral calculus and diffie-q. The forces on the object change as the object's mass changes. So it's a situation where F equals ma, the mass is changing. They make for interesting questions. But alas,